So the topic of my presentation today, rupture styles and recurrence patterns in seismic cycles linked to physical properties of the fault zone. So thanks to the advanced observation methods, people start to notice that rupture events can behave in very different ways. Sometimes they are fairly harmless and they ruptures a little bit faster than the plate rate for a long time. And they don't generate seismic waves to cause damages, and they are so-called slow sleep events. And this happens commonly at the down dip of the seismogenic zones and can only be detected by GPS stations. And sometimes they can be devastating, rupture very fast in seconds or minutes, and cause very strong ground motion by seismic waves. And these rupture events are, as we know, earthquakes, and can be observed by seismic stations. And the rupture style can actually be different. Either it can be crack-like or pause-like. And furthermore, in some cases, seismic and GPS phenomena can actually be co-located, like tremors and low-frequency earthquakes. We call it LFEs, I believe, and VLFEs. They are slow earthquakes. They're seismic phenomena, but they always occur with the slow sleep events. So in the meantime, now as we have more seismic catalogs, thanks to a more complete paleoseismic records, and we see that the earthquakes tend to recur in very different ways as well. So for relatively isolated simple structure faults like this Alpine fault in New Zealand, earthquakes tend to occur periodically. But the majority of the faults don't behave well like that. The recurrence pattern can be super aperiodic with super cycles. So meaning several earthquakes clustered in time. And also not just the time period, the rupture area and the sleep produced by the events are largely different, like this, this figure shows the West Sumatra super cycles. And this, we call them uncharacteristic sleep or dissimilar sleep. And here we use numerical models to try to figure out the underlying relationship of these different phenomena, including different recurrence patterns, different rupture styles like pause and crack-like ruptures, and co-located slow earthquakes and slow sleep events. And we use this multiplicative form of rate and state friction law, where tau here, I believe, is the shear traction, and sigma bar is the effective normal stress. And mu naught is the reference friction coefficient. V and V naught are the sleep velocity and reference velocity. And L is the characteristic weakening distance. And the theta is the state variable, which evolves by aging law in our models. So it is similar with a logarithmic form of rate and state. Here we have A smaller than B represents velocity weakening, and A larger than B represent velocity strengthening. So for velocity weakening, we have ruptures nucleate in this area. And I also want to introduce two non-dimensional parameters, RU and RB. So in later part, I'm gonna explain how they work together to control the rupture behaviors, as I mentioned before. So the first one, the Dieterich-Ruina-Rice number, RU, is actually it's the ratio between the asperity size W and the critical nucleation size H star. And basically, RU number controls the complexity of the ruptures. And RB number here reflects the velocity dependence. So positive RB means velocity weakening, and negative RB means velocity strengthening. And first, we focus on RU number now. So we'll fix RB number as 0.28 for velocity weakening domain. And we explore how RU number controls the complexity of the rupture behaviors. So here is our model. We conduct a 2D strike slip fault with a low velocity fault zone, and this low velocity fault zone has a rigidity of GC and the thickness of T. And we use a spectral boundary integral method for quasi-dynamic approach and with adaptive time steps, by the way. And the right side plots here are the simulated sleep cycles. So here for x-axis are the distance from the fault, and the negative 2.5 to 2.5 kilometers is the range of the velocity weakening. And the y-axis here are the time steps. It's not time, it's time steps. And so I'm going to use this kind of color bar throughout this presentation. So the bluish color here represent the velocity that's around the loading rate. And the yellowish here and here means aseismic ruptures, slow sleep events. And the reddish ruptures are the earthquakes. So from upper left, this one, to the bottom right models, both we have characteristic weakening distance L and the fault zone rigidity decrease. So based on the definition of RU number, RU increases from here to here. Then we see that this rupture style vary by the increasing of RU number from this constant speed creep to creep waves, waves of partial coupling, to aseismic slow sleep events, to bilateral ruptures with the same size, to unilateral ruptures, same size again. Then we see full and partial ruptures with this one and the small partial ruptures. And then we start to see aftershock sequences here with, but this one's crack-like ruptures, and then we eventually got pulse-like ruptures with this large RU set. Excuse me. Then we use 525 simulations to conduct this phase diagram of characteristic weakening distance L and compliance level. So the compliance level here is the ratio between the bedrock rigidity G and the fault zone rigidity GC. So x-axis is L and y-axis is GC. And the color here is their peak sleep velocity. And every dot here represents one simulation, and we use different shapes to describe their rupture styles, whether it's creep, slow sleep events, or bilateral ruptures, or some chaotic cycles. And we also use this shading color to describe that they're the likelihood of pulse-like ruptures. And we see that either by decreased L here or decreased GC, the rupture style is increasingly more complex. And this trend follows the increase of RU as well. So from here to here is the increase of RU. And so the contours here are their RU numbers, and based on these contours, we can tell that the rupture behavior roughly follows their RU number. So in other words, similar RU models yield similar behaviors. If they're on the same contour, they behave similarly, even though they might have different L and different GC. So we picked the example of transition from crack-like to pulse-like rupture. So previous study shows that the highly damaged fault zone promote pulse-like ruptures and back propagations. And so by definition, crack-like rupture, this one, is the type of rupture behavior that the rupture just keeps going on and the sleep keeps accumulating until it reaches the edge, and then it stops and generate this healing phase or stopping phase. So the duration of the sleep, known as the rise time, can be comparable to the total rupture time. And the opposite rupture style here is the pulse-like rupture. It means that the rupture actually self-heals on the rupture back that make the rise time much shorter than the whole duration of the rupture. And we see that we have similar results with the other studies that a crack-like rupture transfer to pulse-like rupture with a highly damaged fault zone, or in other words, reduced GC. And we also see these back propagating ruptures as well. But we also see that the decreased L characteristic weakening distance can do a similar work to transfer crack-like model to this pulse-like model. They are not necessarily like completely the same, but they are similar. So this transition is actually achieved by increased RU number, either obtained by a decreased characteristic weakening distance L or a decreased fault zone rigidity GC. Okay, and to hammer this point that RU controls the rupture complexity, and also to explore the effect of the fault zones better, we then conduct different models with different fault zone thickness and compliance level, and plot all the models here on these two phase diagrams. So the x-axis here are all their RU numbers, meaning that if they plot on the same vertical line, no matter what parameters they have the same RU. And the y-axis here, the left side, is the compliance level. And the right side is the relative thickness, meaning that the thickness over the width of the fault. So from this, we can tell that RU number predict the model's complexities well, because we see that models with similar RUs tend to behave similarly here with different fault zone parameters like different thickness and different rigidity. So here, interestingly, we didn't find any special rupture styles for fault zone in our model. And so I assume it might caused by a quasi-dynamic approach, which ignore the seismic waves. And in real world, fault zones can actually produce a lot special things like seismic phases, like head waves or trap waves. And these can potentially interact with the fault dynamics that cause different complexities, like, I don't know, alternation of hypocenters also. And another thing that I think is worth to address here is that, as I mentioned, RU is the ratio of asperity width W and critical nucleation size H star. And here we use a effective critical nucleation size, which accommodates all the parameters of fault zones, like thickness and GC and L and A and B. So I've explained how RU number controls the rupture style. And in detail here, we pick 4 models from low RU to high RU. We have bilateral ruptures, full and partial ruptures, crack-like ruptures with aftershocks. Then eventually we have a pulse-like ruptures. And we also found that these different rupture styles result in different recurrence behaviors. Here, this middle column is the earthquake time history. X-axis is time, now it's time in years, and the y-axis is the moment. And the stars and triangles are major and minor earthquakes. And the right side are the associated sleep deficit. So we see that bilateral ruptures yield a purely periodic sequences. And with this full and partial rupture, it shows another kind of periodic behavior with 2 large and 2 small earthquakes in one cycle, and every cycle just looks the same. So we call it periodic 4 sequences. Then the sequences become more random when aftershocks involved. And I believe it should be related to some stress perturbation caused by small ruptures. But for a crack-like model, it is still, we call it quasi-periodic, because we calculate the COV number of this model following the standard paleoseismic process. And so the COV number is the standard deviation over the mean of the recurrence time. And people treat anything that below 1 is still periodic or quasi-periodic. But the pulse-like rupture sequence here result in, we can tell that in random sequences, and even we see this clustering of seismic events and here, which is pretty similar to what happened in nature. So similar thing happened for spatial recurrence as well. So a little bit explanation of time and spatial recurrence. Time recurrence means if the earthquakes occur periodically in time or not. And spatial recurrence means when earthquakes occur, do they rupture the similar area and produce similar sleep, or they don't? So here we calculate COV to describe the time recurrence and the proportion of full ruptures, like how many full ruptures, the proportion of that as a proxy of spatial recurrence. And they are the sleep histories. So x-axis are time again, and the y-axis are distance on fault. And the meaning of the star and triangles here are the same with the time recurrence plot, but here they also represent the hypocenters. And the lines here are the rupture area of the earthquakes. So dark blue means full ruptures, and light blue means partial ruptures. And similar with the time recurrence, when we see an increase of RU, the spatial recurrence transfer from completely characteristic, meaning all ruptures are the same time, they're all full ruptures, to excuse me, to dissimilar sleep. And here we have 65% of the ruptures are full ruptures. And we see a lot of them are partial ruptures. Oh, am I drawing something? I know this percentage, 65% is still pretty high, but remember that these models are on a isolated 2D planar fault without any structural or stress field complexity. And it can be dramatically more complex adding more factors or having a fault zone, having a fault system involved. Can I just copy this? So now we understand how the RU number controls the complexity of the rupture patterns and recurrence behaviors, and we then bring RB into our experiments and explore its effect as well. So the motivation of exploring RB in our study is this worldwide concurrent slow sleep events and slow earthquakes. It is pretty common. It has been found in different tectonic settings, like the major subduction zones, like Nankai Trough, Cascadia, and also on strike slip faults, like San Andreas Fault. And black dots here are the location of the tremors, the slow earthquakes, excuse me. And the colored patches are slow sleep events. And we can actually tell that they overlap each other very well. So we were puzzled by this phenomenon because it shows that these two rupture events, even though one is aseismic, one is seismic, are mechanically coupled because they tend to occur at the same time and the same place, both down dip of the seismogenic zones. But based on our current experiments here, it cannot explain this because first, aseismic events and seismic events, they are two mutually exclusive domains in this phase diagram. And second, the slow sleep events here can be accommodated by a very narrow range of RU here, which is unable to explain why it is so common globally. So that's why we believe it is time to introduce RB here to fulfill the whole picture of rupture behaviors. And so inspired by the truth that most concurrent slow sleep events and slow earthquakes take place at the down dip of the seismogenic zone, which is actually the transition from the locked seismogenic zone to unlocked creep area. And this condition is the velocity weakening to velocity strengthening under Riemann state framework. So we propose the idea that it is we call near neutral mechanism here. In other words, RB approaches zero that result in this correlated behaviors. And it helps to explain why it is very common because so no matter what tectonic setting it is, there must be a specific depth range where velocity neutral take place to accommodate transition between weakening and strengthening. And so another physical condition that we use for this model is that because this area have a low permeable seal on it and causing a high pore pressure here, then we make the effective normal stress relatively low. So here we conduct another phase diagram now with both RU, the x-axis, and RB number. And we still, here we use a similar model, still 2D homogeneous model. And we don't use a fault zone model here because we see that fault zone models didn't really contribute interesting new behaviors in our simulations. And still a planar fault with a single velocity weakening asperity in the middle. And again, we see from low RU to high RU, we see that it controls the complexity again. And so basically the previous part of our study, the exploration of RU describes this dashed line here with RB equals 0.28. And now we see a more complete view of how these two non-dimensional parameters, RU and RB, work together to control the rupture behaviors. And as we proposed, now we focus on this whole domain where RB is close to 0. So in this phase diagram, we identify four subdomains here. So first domain that I'm going to introduce here is this. Remember I said that this big bluish area, it means creep or creep waves. So the nucleation is limited by the boundary of the asperities and result in either constant speed creep or creep waves or waves of partial coupling. So creep waves or waves of partial coupling means that the creep speed can be faster and slower over time, and they're just extra long-term slow sleep events. So the second domain here is this big reddish area. So the color still means their peak sleep velocity. This area is the earthquakes, and which we focused on in previous study. And now we focus on the other two phases of slow sleep events. The first one is this whole yellowish area, banana-shaped yellowish area, which is we called aseismic slow sleep events. And these slow sleep events are generated by a low RU, relatively low RU numbers, and the range of the RU number here is dependent on their RB number. And so these slow sleep events are found in nature as well, in between collocated slow sleep events and tremors and seismogenic zones. In some subduction zones, they call it long-term slow sleep events. And while the other domain here, which is what we're interested in now, shows us seismogenic slow sleep events, we can tell that it is way more complex than the aseismic ones, with fast subruptures embedded in slow ruptures. So it explains the mechanism of collocated fast and slow sleep. It is hard to tell from their peak sleep velocity here because well, they have fast ruptures, so their peak sleep velocity should be the same as earthquakes. And the requirement of this seismogenic slow sleep events is very low, near 0 RB, but high and large range of RU. So here is the logarithmic plot of RU. And ideally, RU can be arbitrarily high here. And which is actually exactly what we proposed, the near neutral condition of down dip of the seismogenic zone. Excuse me. And although the models of low RB and high RU explains the collocated slow and fast sleep, it is not suitable to explain the phenomena of seismic tremors because tremors are more specific. It is a cluster of tiny distributed seismic sources. And if you look at their seismograms, and you should see no clear arrival phases like P wave or S wave arrivals, and you should see a train of signals. And here we then add several velocity weakening asperities into this homogeneous near neutral model to mimic tremors and slow sleep events. And we see that the sleep of the heterogeneous model is way complex than the seismogenic slow sleep events. And when the rupture front of slow sleep events pass the asperities, they trigger these tiny little seismic events. And also these little events disturb the propagation of the slow slip events, then trigger the secondary front, and the secondary front trigger more seismic events and get more secondary front, and they go just back and forth and make this slow slip events very complex, and it generates tons of small seismic events. So we also want to know how similar these tiny little seismic events are with tremors. And we choose a set of events as the frame show here. And we set up a seismic station set, which contains 16 stations with the same azimuthal angle. And we calculate the synthetic seismic waves recorded by these stations. And so unlike typical earthquakes here, it is very hard to mark the P and S arrivals because the events are just too close in time and the signals cluster together, which makes them very tremor-like from my view. Okay, so here is my take-home messages. The non-dimensional parameters RU and RB controls the rupture styles jointly, and accompanying a change of rupture style, the recurrence patterns evolve from periodic and characteristic to apparently chaotic cycles. And the effect of complying fault zone in quasi-dynamic simulations can be approximated by a larger RU number. The velocity neutral frictional condition found near the boundary of the seismogenic zone naturally generate SSEs and corresponding slow earthquakes for a wide range of frictional properties. And the hypercenter of slow earthquakes clustered both in space and time and is located at the rupture front of the slow slip events. And that's all I have today. Thank you again for your time and attention, and feel free to ask questions.